Octopuses represent a fascinating example of how intelligence can evolve along an entirely different path from tetrapods. In tetrapods, intelligence emerged layer by layer, building on a foundation that began with fish. Fish, as swift and agile creatures, evolved to have their sensory organs directed forward, towards the front of their bodies, enabling them to navigate their environment and feed efficiently. Their spine, acting as a central hub, connected nerves throughout their body, enabling quick reflexes, a vital trait for both evasion and predation. This need to react rapidly as they gained speed in the water gave them an early boost in brain power. When these fish made the leap from water to land, they faced a three-dimensional world that required even more mental agility. Movement on land was far more complex, involving interaction with various terrains, rocks, soil, bushes, tree branches. This forced tetrapods to increase their brain capacity further, as they needed to balance, maneuver, and interact with an environment that was no longer fluid. Hunting on land, particularly chasing prey that could turn and dart unpredictably, along with foraging in this varied landscape, further honed their cognitive abilities. Then came a major split. Many tetrapods began to care for their young. Unlike their aquatic ancestors, who could scatter countless eggs and sperm to fend for themselves in the vast ocean, land-dwelling creatures often needed to protect, nest, or even give live birth to fewer offspring. This nurturing behavior created another layer of social complexity. And once they became social, some tetrapods took it to the next level, forming packs, developing intricate social bonds. Sociality became a driving force, pushing intelligence even further as it required communication, hierarchy, and cooperation. From there, new challenges, flying, climbing, evolving more advanced movements, demanded even more from the brain. Different regions developed to handle these demands, but fascinatingly, these same regions could also co-adapt for other purposes. Intelligence gained for social interaction could also be used to interpret the environment, while sensory systems could feed back into social behavior. Eventually, this convergence of traits and pressures gave rise to the most intelligent tetrapods we know today, birds and mammals, especially primates. But cephalopods, specifically cuttlefish, octopuses, and squid, followed an entirely different evolutionary path. Unlike tetrapods, cephalopods didn't have a sophisticated lineage of fish to build upon. Instead, they had to evolve their intelligence from a far more primitive starting point, the ancestors of modern-day cephalopods, which were much closer to simple slug-like creatures. Their evolutionary story began with organisms that were akin to the early bilaterians, or their successors, the nephrozoans. These creatures, though groundbreaking in their own way, were incredibly rudimentary, possessing only the most basic life systems. Imagine the concept of a transistor in computing: small, simple, but foundational. These early creatures had a simple gut, sensory organs, a rudimentary brain, and muscles, the bare essentials for survival. Unlike tetrapods, cephalopods didn't have the benefit of building upon complex systems of sociality or advanced motion. Instead, they had to start from scratch. They evolved from shelled ancestors, far more basic in structure than the fish that gave rise to tetrapods. If you look at modern snails or slugs, you see remnants of this early simplicity. These creatures have the essential four systems: sensors, a basic brain, a chewing mechanism, and muscles, but without the interplay and coordination that would come much later in evolution. Cephalopods, however, pushed this rudimentary foundation to incredible heights. Through separate, distinct pressures and innovations, they independently evolved their intelligence to match, and in some cases surpass, many vertebrates. Their journey, though different, highlights the diverse ways evolution can shape cognition, even from the simplest of beginnings. The future evolution of octopus intelligence presents fascinating possibilities, particularly in how their neural structures and cognitive abilities could develop. Currently, octopuses use RNA editing to adapt to their environments, and in the future, they may evolve the ability to consciously perceive the genetic changes this process brings. This could lead to the remarkable possibility of octopuses accessing the memories of their ancestors, seeing images, hearing sounds, and even experiencing thoughts and feelings passed down through generations. If octopuses gained access to such inherited memories, it would offer them a new dimension of intelligence. They could draw on a wealth of ancestral knowledge to rapidly adapt to challenges and changes in their environment. This might lead to cognitive abilities that surpass even human intelligence in some ways. However, unlike humans, whose intelligence is deeply tied to social structures, octopuses may remain solitary creatures. Their intelligence would likely focus on individual adaptation and environmental interaction rather than social collaboration. In this way, octopuses could evolve into highly intelligent beings, but their form of intelligence would remain fundamentally different from ours. Their ability to adapt through both environmental cues and inherited memories could lead them down a unique evolutionary path, one driven by solitary mastery of their dynamic ocean world.